Okay, as I discussed, I'm going to talk now about what happens if I'm going to get sodium bicarbonate, the amphiprotic substance, and I'm going to get it to act as an acid or a base in this titration by titrating it in case 1 with NaOH and in case 2 with 0.2 molar HCl. So, NaHCO3 is going to dissociate into Na plus and HCO3 minus. And on its own, in natural water, that HCO3 minus can engage in two possible reactions. It can react with water as an acid to form H3O plus and CO3 2 minus. The K for this second proton process, or the Ka2 for this acid, would be 4.7 times 10 to the negative 11. Meaning that this reaction does not happen very often. That's getting pretty close down to Kw, and that's a very small Ka. Or HCO3 minus can react with water to form OH minus and H2CO3. The Ka for this reverse process, where it gives up that H, so the Ka for this process here, H2O or H2CO3 plus H2O goes to H3O plus and HCO3 minus. So that's the inverse process of this. That Ka, or the Ka1, is, I'm going to find them here, no, that's not right, 4.4 times 10 to the negative 7. So to judge how likely this process is, we need the Kb for the conjugate process, and we remember our relationship that Ka plus or times Kb is equal to Kw. So 4.4 times 10 to the negative 7. Kb, I don't know. That's what I'm finding. And the Kw of 1 times 10 to the negative 14. So Kb 1 star is 2.3 times 10 to the negative 8. So the Kb for this process, Kb1 star, is equal to 2.3 times 10 to the negative 8. So this one is about 3 times bigger, or about 1,000 times bigger. So what that means then is in distilled water, this process happens a lot more than this process, which means that HCO3 minus behaves as a base way more often than as an acid. So what that means then is the pH, which is going to depend on how much NaHCO3 is put into the substance, is going to be somewhere on the order of 9 or so. So what we're going to do now is we're going to react it to its equivalence point with the two substances, and then we're going to see where those two equivalence points are, and we'll get a sense of what our titration is going to look like. If we want to view that this way, if I want to say this is adding my acid and this is adding my base, then if I don't add either, I'm starting at a pH around 9. And let's see what happens as I add base and as I add base or acid. So it looks like we'll do base first. So let's just get this. I got 20 milliliters of 0.2 molar HCO3 minus. I have 20 milliliters. Yeah. 0.02 liters. And the concentration is 0.2. And I'm going to react that with NaOH to produce H2O and Na plus and CO3 2 minus. At equivalence, I want the moles of my NaOH to be equal to the moles of my CO3 minus. So using C equals N over V, then I go N equals CV. I can get my moles of HCO3 by going 0.2 times 0.02, which gets me 0.004 moles. And that means I have 0.004 moles of my NaOH. I need my volume of that, so I have to keep going with this. My concentration was 0.2 molar. So those are equal, which means my volume is just going to be equal, and I'm going to need 20 milliliters, but I'll just do the calculation anyways. Volume equals N over C, which would be 0.004 divided by 0.2, or 0.02 liters. Okay, now this acid-base reaction, as all of them do, go to completion. So minus 0.004, minus 0.004, using those up completely, that's why we call it the equivalence point, and making 0.004 moles of our CO3 2 minus. This H2O is water, so we're not interested in it from an acid-base perspective, and this Na is the conjugate of NaOH, so since it's the conjugate of a strong base, we're not interested in it either. So now I need the concentration of my CO3 2 minus because I'm going to have to do that equilibrium calculation. Careful here, I had 0.02 liters of this and 0.02 liters of this, so my volume total at equivalence is 0.04 liters. So my new concentration, 0.004 divided by 0.04, is 0.1 molar. Now I can do my equilibrium calculation with CO3 2 minus. CO3 2 minus is going to act as a base in solution, making HCO3 minus and OH minus. We have a starting concentration of this of 0.1 molar. Don't care about him. And we have none of this, and we're going to ignore the native population of that. So the Ka for this forward process is 4.7 times 10 to the negative 11. So the Kb we can find using our relationship. It's going to be a pretty strong process this time. 1 exponent negative 14 divided by 4.7 exponent negative 11. And I got 2.12 times 10 to the negative 4. Okay, now the change in this is going to shift to the right. I'm going to produce 1x and 1x of these because they're in a 1-to-1 ratio, and I'm going to use up an x of this. 0.1 divided by my K value is 470, which is greater than 100. So we can use the 100 rule, which means when I'm considering this 0.1 minus x, this x value is small. So I can simply consider this 0.1. This is x and this is x. Again, initial change equilibrium. So now I can write my Kb2 star K expression. Here I have HCO3 minus on the top, OH minus on the top, and concentration of CO3 2 minus on the bottom. So x 0.1, and what is it, 2.12 times 10 to the negative 4 from right there for the K value. So 2.12 exponent negative 4 times 0.1, square root that. X is equal to 4.6 times 10 to the negative 3. That'll allow us to calculate our pOH value. Because it is the concentration of OH. And I get 2.34. Then I can use my relationship between pH and pOH to find my pH. And I get 11.66. So, half of the problem done here for our titration. If we started at 9 and we start adding base, it's going to creep up until it hits an equivalence point, and then it's going to curl over, and that equivalence point is going to occur at a pH of 11.66. I think I'm going to stop us here and come back and finish off this video where I look at the acid as a separate video. So I'm just going to pause right here and then come back and do the other half of this in a secondary video.